Hey guys, welcome to the lab 2 of this course. Today we will discuss a couple of crucial concepts such as partitioning and explore a variety of tools for meshing techniques and how to visualize your output in a various viewports. Okay, so in this example, we will model an open hole tension coupon. Okay, that's basically a tensile coupon with a hole in it. And we'll study what the effect of the resultant load and displacement profile is based on what the hole size is. So let's go ahead and first make sure that our work directory is set. I wanted to set to my Abaqus folder in the documents. Remember, today I'm working in the remote lab system. The only difference between remote lab system and your own personal copy of Abaqus, the student version on your own computer, if you have gotten so far, is that your copy of Abaqus will only allow up to 1,000 nodes to model at a time. You could mesh more than that. You just won't be able to run the analysis when you submit the job. So if you have a good internet connection, I would recommend working on the remote lab system. If not, you could do a workaround. So you could work on your own Abaqus model and save the CAE file, carry over that CAE file to the remote lab system and open that into the Abaqus that is here on the remote lab system and run the job from the remote lab. Okay, hopefully that was clear. I'm going to hit OK. And the very first thing that we're going to focus on today is to locate Rpy file. So generally, a default Abaqus directory, if you haven't set so already, would be a temp directory. Okay, that would be in your C drive under the temp folder. And this is my Rpy file. And you want to make sure that you open your Rpy file with Notepad++ program. Okay, and I've installed that on my remote lab account. You could do the same as well, just to make sure that you select edit with Notepad every time. Okay, and I already had that open, so it asks me that the file has been modified and I want to reload it, and I'm gonna click yes. And that is the very the big reason that I want you to use Notepad++ is that it will automatically update the file as needed. Okay, so what this file does is it records everything I do in Abaqus. So if I create a part, it will have a set of commands that creates a part, and it will write down those commands in this Rpy file, and hence this Rpy file will keep updating as you do something in Abaqus. Okay, so let's go ahead and create a part and see what happens. Create a part. I'm gonna name it open hole tension. Hit continue. I'm going to create a rectangle of size 20 by 50. So let's put our first point on 0, 0, the origin, and the second point on 20, 50. Okay, hit auto fit. And then I'm going to create a hole in the middle of this rectangle, hence the open hole tension coupon. I'm going to locate that at 10 by 25. And then it asks for me to pick a perimeter point of the circle. I ideally want the radius to vary between, let's say, 5 to 8 millimeter. So I'm going to start with 5 millimeter radius. That means it will be about, the second point would be on, let's say, 15 by 25. And that is my 5 millimeter radius. I'm done with the sketch. I'm gonna get out of it, hit OK, hit done. And I want the depth of this profile to be 3 millimeters. Hit OK, and this is our part ready. Okay, now if you go back to your Notepad++ in abaqus.rpy file, it says this file has been modified. Do you want to reload it? And hit OK. And now you have a set of commands that shows that you created a sketch and created a part from that sketch. And I'm going to copy those commands, copy all of those commands into a new file. And into the new file, and I've named that file oht.py and saved it into my documents Abaqus folder. Okay, paste it. And now you see that the extension of this file is py. That stands for Python language. Okay, so all the coding for Abaqus is done in a Python language. Okay, so keep that in mind as well. So far, we are just trying to copy what Abaqus is writing here into our Python file, because all those commands here are the Python commands. Okay, so let's go ahead and define our material. Go to property. I'm going to define the same material as last time. Create a section. I'm going to name the section as OHT. Hit continue. The section is defined for the material steel. Hit OK. And I'm going to, let's say it asks me to select the regions to be assigned to a section and simultaneously also creates the set. So that's a win-win for me. I'm going to call that set OHT, select the region for that set to be this, hit done. And then I'm assigning the section to this set right here and hit OK. Okay, now next thing, let's assign the material orientation, and for that create the material orientation. I'm gonna name it custom one. Hit OK. I would just want the orientation to be the same as the global one, and for that I don't need to change anything or define anything extra, so I'm just gonna hit on create datum and get out of there. Let's hit on assign material orientation, and you want to go to your set OHT and hit continue, and then select the custom CSYS that you have defined, hit OK, and select the defaults, hit OK, and the orientation is now assigned. Okay, so next step is I want to look at my mesh. I want to see what the mesh looks like with the default option. And I'm going to see in the front view. So hit on this option right here, seed the part with the default options, and mesh the part. Ow. So it looks very irregular arrangement of elements. And if you were to just perform your analysis on this with the appropriate boundary conditions, you will see stresses or strain distribution that is not so regular. And as you can see, this model is symmetric. It should be symmetric, right? So the mesh we want as symmetric as possible, depending on the geometry. Okay, so I'm going to allow for that, I could either go ahead and partition the geometry into multiple different partitions such that each partition is meshed separately, and hence allows to maintain the regularity and the symmetry across the domain. There is also another option that I could use, is that I could also use a different meshing algorithm, okay, and that is done by mesh controls. So let's go to our mesh option, and there is a very first option is called controls, and that basically defines how the meshing should be done by Abaqus. And has various options of element shapes. I want to keep all of my elements to be the same type, such as hex. Hex means element with 6 faces, which means a cuboid or a just call an hex element. Another one could be like a pyramid shape element, which is a tet element. So you could go with the mix of elements which is given by hex dominated, which mostly will mesh in a hex element, but at some parts of the regions, they will allow the tet elements or wedge elements to be there. So for just the hex elements, there are 2 algorithms with the 2 techniques, the sweep and the bottom up. Right now, we are going to focus on the sweep technique. And by default, Abaqus has chosen advancing front. And it's generally not a good choice for this type of geometry. So I'm going to go for medial axis that allows us to minimize the mesh transition. So mesh transition meaning from regular looking mesh to mesh that looks something like this. You're minimizing going from the regular to the irregular mesh. So let's hit OK, and it will ask us to delete mesh because it's going to create new one. And with the same seeding, I'm going to mesh the part again. And as you can see, it has made it much better, more symmetric, although there are still some parts of the mesh, such as here and here, are not so symmetric as compared to on their counterparts on the other side of the domain, right? And further, like the elements over here are a little bit squishier than the elements up top and the bottom. So if you want to regularize the mesh in order to get a better solution, remember we have talked about stiffness matrix and how the stiffness matrix inversion or the process of inverting can be cumbersome if there are elements of the stiffness matrix such that they are too small or too big as compared to the other one, then we will have hard time getting a solution that is more accurate. Okay, so you want mesh to be as much as uniform as possible. So to achieve that, let's go ahead and partition our part. But before we do that, let's check our Rpy file. Now it has been modified. And all the processes that we did, such as creating a material, as you can see here, creating a section, and creating the CSYs, the coordinate system. What else is there? Yep, all those commands are there in the highlighted section right here. So I'm going to copy those commands and paste into my py file. And I can also comment each file, each step, such as in this one, I'm creating a step. I'm going to I'm gonna write create part. And since this is a comment and it's not a part of a command, I want to comment that line out, and I can do it by this option under edit. It says comment or uncomment, and I can select the single line comment option, which is Control K. And alternatively, you can also write hash in front of every line that you want to comment. Generally, I like to comment by selecting the whole block. If I want to make it inactive in the code, I can just select it and comment it all together by that option. Okay, so commenting is a one way to ensure that you are separating those different sections when you are defining the different parts, different modules and the model. So the next one is defining the material and assigning the material and so forth. So I'm going to write here create material. Let's say the next one is creating a section. And so on and so forth. And you can recognize all the different commands from there. Okay. One benefit of doing that is that I can then look at the part of the code where I've created a part. And if I wanted to modify, for example, the radius of the circle, then I just have to modify this parameter and I create a variable or modify this parameter and rerun the script in Abaqus to create the whole model. Okay, so I'm gonna save this. After this part, I played around with the mesh, and which I don't want to import just now because I'm still modifying the mesh. So I'm going to go ahead and delete the part of the code in my Rpy file that performs the mesh option, okay? Because I just don't want that yet. Select that script. Go back to my Abaqus. And now I want to go back to my part and partition that part. Okay, so hit on click partition. There are three ways to partition a part. It can be either edge, face, or cell. So cell means the whole 3D body of the part. So the entire 3D. Edge meaning this one edge or edge of the circle that's being defined, or the small edge perpendicular to the plane, anything. Face can be any 2D surface that you see in your model. Could be a face. But today I want to partition the cell. And I'm going to use a method of define cutting plane. And as soon as I do that, it asks me to delete the mesh because now the mesh will be dependent on the part that was original part. And if I just because I'm partitioning the part, the mesh is no longer valid. Okay, so I'm gonna delete that. I'm choosing the method of point and normal, in which I can select a point. And select a normal direction, which is normal to the cutting plane. Okay, I want to cut the part in the two segments, one horizontal going through the circle and the vertical going through the circle. So I'm going to right now select a point that will be on the cutting plane, which is this point selected by red. And I want the normal, which is, it can be this edge or any parallel edge to this direction. And I'm going to hit create partition. Okay, now I want to create the vertical partition, and for that I'm going to simply select both surfaces, both cells. Now we have two cells because we have created a partition, and hit done. And I'm going to go for point and normal, and click on a point that you want it to be on a cutting plane. This is the point I want, and then I want to select the edge that is perpendicular to that point. It can be any horizontal edge. Okay, create a partition, and there you go. You have created 4 partitions with the 2 partition techniques. Okay, once we have created partitions, let's go back and check our code once more. It will have lines of the code related to the partitioning. Okay, so I'm gonna select those and copy them after the section assignment. And I'm gonna write a comment that here I'm creating partitions. Okay, now after creating a partition, it will allow us to create more regular mesh. So let's go to our mesh module and seed the part again. Apply. I'm going to make it a little smaller seeding. It is okay to mesh, and you can see The mesh is much more regular and much more symmetric than the previous version of mesh. You could also make it more symmetric by even creating a diagonal partitions that goes at a 45-degree angle instead of two perpendicular ones, in addition to these two perpendicular ones. And more partition you create, more symmetry you achieve in your mesh. Okay, so I'm happy with the mesh I have right now. And I'm now going to go back to the file where the mesh part is updated. And I'm going to select that code. And comment here that I'm creating a mesh. Okay, and save it. Okay, now after that, everything else is pretty much similar to the last time. I'm going to go to my assembly, create assembly, create an instance. I'm also going to, first of all, create sets for my boundary conditions. Okay, so let's go back to part, go to tools, create set. I'm gonna give bottom face, select that bottom face. And now we have two sub faces of that bottom face. So select multiple faces. You will hold down the shift key on your keyboard and click on both the faces. Okay. And similarly for the top face. Create set by clicking on this. Top face. Okay. Similarly. Okay. Okay. One more thing I'm going to do here is that I'm going to define a reference point. A reference point is a common practice in the cases where you want to calculate the total force acting on the load face. For example, if I were to apply boundary condition directly on this top face, and I want to know at the end of the day what my total load on that face is, I would have to extract the force from each node on that face and sum it up to get the total node force. Alternative way is to define a reference point. Reference point is then tied. It's a virtual point. It's not a real geometric point. It's something that on which the load is applied, and then the reference node is tied to the surface of your loading phase, and such that the loading phase moves it's the same amount as the reference node. And this technique allows us to just calculate the load on the reference node or the reference point, and that would be the total force acting on the entire load phase. How cool is that? Like that way we don't have to do any post-processing work. We just extract the force from the reference point. Okay, so let's go ahead and create the reference point. The second option is a reference point, and you can virtually select any point to be a reference point. Doesn't really matter, but to make it more easy to keep track of, I'm gonna select a midpoint of my top face. Okay, and that appears as a RP right here, and it's just some arbitrary point, a virtual point not existing on any geometric surfaces. Okay, and then I want to create a set for that reference point, and I'm going to create a set. I'm going to name it RP for reference point. Okay, and it's a geometry. You can hit continue and click on that point. It will highlight right here and hit done. Okay, so now you have reference point, you have all the sets for bottom, top face, and the reference point itself. So now we're gonna go back and define a constraint that ties the top face to the reference point. So for that, we'll go to interaction. And under interaction, I'm going to click on create interaction. And for that, let's create another type of interaction, that is create a constraint that is more suitable for this type of problem. And I'm going to create an equation constraint. Okay, so let's create an equation constraint, and I'm going to name constraint in y direction. Okay, and hit continue. Now to define constraint, I'm going to refer you to the Abaqus help. If you click on help option here and click on module, you will end up to an Abaqus help site. You may have to log in with your account, but after you log in, the Abaqus help is free. Just not sure why they want you to log in, but they do want to log in. Okay, so in the interaction module, then you want to click on understanding the constraints, I believe. And understanding the constraints, you will end up going to the equation constraint and click on the linear constraint equations. And if you go on the linear constraint equation, you can see how the constraints are defined, why the constraints are defined, and so forth. It's in the form of a linear equation. For example, here the equation looks like that. U3 means the third displacement, the z displacement of node 5 is equal to the first displacement of node 6 minus the third displacement, the uz of 1000th node. Okay, and then you can bring all the terms towards the left-hand side and have the 0 on the other side, that this is the form you want to implement your equation in. So in my case, I want to have the constraint such that it constraining the y displacement u2 for my reference point, and constraining the y displacement of all the nodes on my top face. Okay, so then here u6 can be for all the nodes of that face as well. So let's try to do that, and I suggest you to write down those equations and see how to implement it. So I'm going to give the coefficients. The coefficients are, let's go back here, see what the coefficients are. The coefficients would be simply the coefficients of each displacement entity. So for the first one, it would be simply +1. Second one is -1. Third one is +1. Okay. So let's go back here. I'm going to first get my set name, the Rp. Okay. The degree of freedom, either it can be 1, 2, or 3. And you can also hit on the tip, and it will give you explanation as well. So there are multiple ways to obtain help in Abaqus, and this is 2 ways I've shown you today. So I'm going to write down my second degree of freedom for which I want to constrain. I'm gonna assign a coefficient 1. This would be -1, and I want the second set to be the top face. I want the degree of freedom too. Okay, hopefully this works. Okay, So this is what I feared. Generally, the order of the set matters. Abaqus prefers using the first a set consisting of a single point, and all the subsequent set also should be single point set. So you want to define the first set in your constraint equation to be the set that has the highest number of nodes, and that are obviously that set is our top face, right? So I want to write the top face as a first set and the Rp point as my second. Okay, and hit OK, and it will create a constraint, and you can see for that constraint it will show up in this tiny circles on the top face. Okay, I not only want to constrain the y movement, I also want to constrain the x and z movement. So I'm going to copy the same constraint and name it as x, and copy the same y constraint and name it as z. So that I just don't have to define all over. I just have to change one thing in each constraint. So I'm going to my x constraint, edit it, and instead of degree of freedom being 2, I'm going to write 1 for x. And similarly for z, I'm going to edit it and change the DOF to 3. Okay, so now we are done with constraint. Let's go to boundary conditions. Oh, we forgot to define a step. So let's go and define a step first. Create a step, load step. After the initial step, hit continue, select all the default options. Now let's go back to the loading step. Okay, I want to create a boundary condition. First one is I want to fix the bottom, and I'm going to select the initial step. So whenever something is fixed in your simulation, try to put it in an initial step. Okay, and go with selection of the bottom face, hit continue, and I'm going to pin it. Generally, you also want to restrict the rotational degrees of freedom, such as UR1, UR2, UR3. Because we have an isotropic material, that doesn't really matter. But if you have an anisotropic material, for example, composite or a crystal structure, you also want to rotate, you also want to fix the rotational degrees of freedom. Okay, hit OK, and that boundary condition is created. Let's go to the new one. I want to go to the load step, name the boundary condition. It's a load top face. Apply displacement boundary condition. Now that boundary condition is now defined on the reference point set. Okay, and remember, reference point is tied or constrained to the top face movement, or the top face is constrained to the reference point movement. So if the reference point moves by 2 millimeter, the top face will also move by 2 millimeter in the given direction. Okay, so I'm going to apply boundary conditions on my reference point. I want my U1 and U3 to be 0, and I want my U2 to be, let's say, 3 millimeters. Okay. After all this, make sure your field output values are the values that you want. So I'm going to check all of them. I'm going to select my total strain. You can also select elastic strain, but that would be the same given the problem is elastic. I want the forces, just the reaction force, and I don't want any contact terms because there is no contact in this problem. Okay, so now let's go ahead and define our job. OHT1, or I'm going to define it by the radius 5 millimeter and hit continue and create a job. Okay, after doing all this, let's revisit our Rpy file. We'll go from the line number 79 onwards in this case. And I'm gonna copy all these commands over here to my oht.py file and hit save. Okay, now I'm going to run or submit my job. And it's going to take some time to run the job. Okay. Okay, now let's check our results. And you can say the deformation has occurred. And then you can play around checking all the different values for stresses and strains and stuff. I want to focus on the reaction force though. So let's check the reaction force could be. As you can see, there is a lot of variation in this legend, but everything else, everything in the model itself is in the blue, which means it has a zero reaction force. And that is because we have defined our reference point on which a reaction force is calculated instead of the entire geometry. Okay, so as you can see, our reference point reaction force is of the order of this magnitude here. The alternate way to check for that is go under Tools and Query, and then you can select on probe values and want to select nodes. And then you would have to go around a little bit to find out which one is your reference point, but the reference point would be the one whose magnitude is non-zero in this window. Okay, so here you have various options, and under this, focus on this where I hover around different nodes. Okay, and for since we defined in the right in the middle, yep, right there is our reference point, and the magnitude is 819,200. Okay, so this now represents our total reaction force value for the entire top face. Okay. Now the next step I want you to do is I want you to modify the radius value in your script file. So go back to your oht.py file, locate the part definition, and I want you to change the value of the radius. For example, current was 5 millimeter. You can now change it to, let's say, 7 millimeter and run the whole analysis based on that and see how the how the reaction force at the reference point changes. Okay, now that I have my Python file created for the model OHT, the Python file oht.py, let's try to change a couple of things. And we're gonna run a parametric study, for example. We're gonna change one parameter for the same model. I'm going to show you the example of how to change radius and how to change mesh size. Okay, and we'll run simulations for various mesh size and various radius of the hole. Okay, so let's try to look at where our hole is defined. This is this very command where the circle by center parameter, that is the command we used in Abaqus CAE as well, where the center point coordinates are this, and the point on the perimeter has coordinates of these. Okay, and now I know that my center is 10, and my radius I wanted to be 5, hence I kept my x coordinate for the perimeter point to be 15. So I can make this a variable by saying that the point on the perimeter, the x coordinate is 10, which is the point x coordinate for the center plus some radius value, and I'll define this variable radius in a bit. And my y coordinate is 25, which is the same as my center y coordinate. Okay, and if you were to draw it on a piece of paper, you'll understand how that comes about. So let's define our variables. Okay, I'm going to define radius by variable rad as our radius, let's say 6.5. Okay, and then I'm going to also define a mesh size. So let's say I'm going to write m underscore size, stands for mesh size. I kept it, initially we kept the seed size for 1. Let's say for something different, I'm going to make it 1.5. Okay, so the first thing to remember is we have defined the variable name is equal to some value, and mesh size m underscore size is equal to some value. Okay, and then you replace that variable with the value that was defined here. Okay, and similarly, I want to change the variable, and I want to implement the variable for the mesh size as well. So I'm going to go to the section where the mesh is defined and find the command where the part is seeded. So that's called p.seed part. Okay, and where the size of the seed is defined as 2.0, and replace that number with the variable m underscore size. Okay, so rest of them does not have to change right now. One thing that if you want to change the job name for each change in parameters such as radius and mesh size, you can change that here under the mdb.job name is equal to so and so. I can then write my name to be, let's say 6.5. I'm not sure if it allows point in the name of a file, so I'm just gonna write 6p file, means 6.5 millimeter. Okay, and I'm gonna say that my mesh size is 1.5. Okay, let's run our script with these parameters. Let me make sure I defined it correctly, 6.5 and 1.5. Okay, looks good. I'm going to go to my Abaqus. If you have a model defined, you want to delete that model. And generally, as a good practice, you want to save the model before you delete the model. And to save it, just go to File and Save As, and then you will save it as a CAE file, just as we did last week. Okay, now I already created a blank canvas for my model. You can always create blank canvas by just clicking on this white page icon, says new model database, and go from there. Okay, and then click on File and click on Run Script. Make sure you are in a correct folder where your script is situated at. So mine is in the Documents folder, in Abaqus folder within the Documents folder. And I can then locate my file, oht.py, and hit OK. And here you go. The whole model is created just based on the script. So now you should be able to appreciate why we do the scripting process. because then we can create a parametric study by easily varying the hole size, easily varying the mesh size, and even the boundary condition if you wanted to vary the magnitude of how far or how big or small the displacement y should be. You can also make another variable for the boundary term and vary that with each analysis as well. Okay, so, and as you can see, for that particular job, this new job is now created, and then you can submit your job and it will run the analysis. Okay, and so on and so forth. You can keep trying different values of mesh size and different values of radius and see how the results change. So I'm going to now try to visualize with the 2 simulations I've run so far. I'm going to go to the results tab and check on my final result. Okay, since this looks way too deformed for me, and Abaqus generally does that. Abaqus has this deformation scale factor that it blows up the deformation to see how exactly the deformation is progressing. So I want to go to my options under common and go to the deformation scale factor here, and I want to set it to uniform and value 1. And if you apply now you see a standard deformation instead of a blown up deformation, excessive deformation that Abaqus tries to show. Other thing you want to change is the font sizes in this viewport. And for that, go to your viewport option, click on viewport annotation options, and then go to each individual tab and change the font sizes. So this is for triad. Triad is this tiny symbol showing X, Y, and Z coordinates. And I want to make those numbers a little big. So I'm going to click on that, increase my font size to 24, hit OK. As you can see, the numbers are increased. Same with the legend. I'm going to increase the font sizes. And depending on your installation settings, this fonts may be by default bigger, then you might not even need to change it, but I had to, so now you know a way to do that. So I'm basically going to each tab and changing that. Okay, hit OK. So now you can see all the details in a larger font size. Okay, next thing I want you to see is that you can create a new viewport. So viewport is basically this area with this dark blue background. I can create another viewport as well. And then I can align those viewport side by side. So then I can tile them vertically together or horizontally together. I'm going to do vertical just because my sample is vertical. And then I can select output from one simulation and compare them to the output of the other simulation in the second viewport. So I only have one results right now. I'm gonna open my previous simulation results. So right click and click on open. I'm going to go to my Abaqus folder in my documents. And click on my previous simulation output file, ODB file, remember that. And click on the front view. And one interesting thing I'm going to do is I'm going to link these two viewports by going under viewport and clicking on link viewport. Okay, so by doing that, every change I make in one viewport will also be visible in the other viewport as well. Okay, so let's go here. Probably have to do something. Yep, there you go. I'm also going to make sure that my deformation scale factor for the second output file that I just opened is the 1. Okay, that makes sense. So here I have comparison of, it's not an ideal comparison, it's a comparison of 5 millimeter versus 6.5 millimeter hole size, and one has a finer mesh and one has a little bigger element sizes. So ideally you want to compare for the same mesh size, different hole diameters, or for the same hole size, for example 5 millimeter, try to vary the mesh size and compare them side by side and see how the profile across the uh, horizontal line along the hole changes. Okay, so that is the task for you this week, is to modify your Python script, and with respect to changing the hole size and changing the mesh size, make sure you also change your job name so that you know what that job is for, what are the specifications, and run simulation for each of those models and compare them side by side. You can create as many viewports as you want and tile them all vertically or horizontally as you need. Okay, so for example, you can tile them vertically like so. Okay, and if your script for some reason doesn't work, I've also attached the script file from my own analysis, and that you can play around with.